Hello, welcome to Everything Distributed. Today we are going to talk about a very important concept, especially in distributed systems. It's called CAP, consistency, availability, and partition tolerance. And there are tons of reference, and the concept of CAP was first proposed by Brewer in Posse. It's in a keynote speech. And then later, 2 years later, Seth and Nancy, they formalized Airy's conjecture and then prove it. So at this time, it kind of becomes a CAP theorem. And but then later, the industry said that, oh, that's pretty nice. We have this kind of theorem. Then we need to build something that kind of can be explained by this theorem, or that we need to apply this theorem somehow in our system. But then there were tons of confusion and then different interpretation. So after 12 years, Eric Brewer said that, okay, I have to kind of clarify something. So we have this one, kept 12 years later, and it clarified lots of misconception, misunderstanding of the theorem. And later on, like Martin, he also give a very critical critique on the CAP theorem. He first went through that what the CAP theorem is, then what's the model, and then what's a divergence from the practical system, what do some kind of mismatch between the model and then empirical empirical like kind of observation. And all of them are very easy to read, and if you are working in some kind of storage or web service, especially in a global scale, I really encourage you to read all four articles. They are actually pretty easy to read. Okay, so now we first start with the very clean and precise model, follow Gilbert and Lynch paper. So CAP, remember that we discussed this concept of this distributed storage system. And one of the simplest form is that it can provide the read and write operation, and it's on a single key value pair. And here in the original the paper, they model consistency as a linearizability, but it can also be used to explain a strong consistency, meaning that when you do a read, you have to see the effect of the most recent complete write. Okay, and then availability. The idea is that as long as there is a correct node or correct server inside the system, then every operation, including the read or write, should terminate. Because that's a very reasonable assumption, because as a client, you want the system to respond to your operation. And then we have a partition tolerance, and that's kind of the new way of formulate the key property by Brewer, is that because when you deal with a distributed system, if you remember what we talk about the network, there are lots of different kind of failure inside the network layer. And then no matter what the cause a problem layer, then on the layer on top of that at the system side, what you observe is that sometimes I cannot communicate with some nodes or some server inside the system. And the way to think about this is that you have a partition tolerance, so that you might have a two set of nodes, they cannot communicate with each other. And in Gilbert and Lynch paper, they model it as a typical asynchronous network, meaning that we between any pair of nodes or any two sets of nodes, there might be arbitrary message loss or delay. Okay, so that's the model, very clean and very precise. Then the CAP theorem, or like at first is a Brewer's conjecture, is that pretty simple to state. Now we have a three very important property for our distributed system. And unfortunately, we cannot achieve all three of them at the same time. Okay. So here is a very simple illustration of the proof idea. Suppose you just have two server A on the left-hand side and then server B on the right-hand side. And then you also have two clients. And suppose one of the client on the left-hand side said that I'm going to write value 1 into key K. And then the way it does is that it communicates with this server. Okay. And unfortunately, now here the network is not behaving well, so we observe partition tolerance. So what that means is that any message going from left to right, either from the server A to this server B, or from this client to the client server B, all of the message are like arbitrarily delayed, or like all of them are lost. And similarly from the right hand side to the left hand side. Okay. Then in this case, suppose the client on the right hand side does a read on key K. Okay. Then because of the message are kind of lost, you don't have any communication from the left hand side to the right hand side, or to the right hand side to the left hand side. So that's partition tolerance. But because our system want to tolerate this kind of partition, then now let's look at what consistency means. Consistency, start with availability. What availability means is that the operation must be complete and successfully completed. So this server will return to this client, say that, okay, your operation is completed, so I have one here locally. And now for the right hand side, the right client will also talk with this server. And because of availability, this operation must be able to complete. Okay, so you will tell this client that, okay, now your operation completes. But because there's no communication between the two group of servers and client, so it's impossible for the server on the right hand side to know it's one. So it must return some like default value to the client, and then the client will say, okay, now this is this default value, so it violates consistency. Okay, and then if you want to argue that this client must need to satisfy consistency, then what that means, let's look at use the blue line. That means that, okay, there must be some communication from left hand side to the right hand side, but then you might wait forever because that there's a partition, and then this the server, this right hand side the server can never respond to the client, and that's why you cannot achieve all three properties at the same time. Okay, very simple ideas. And if you read the paper, actually the proof is just like maybe 1 page long, and it's very easy to follow. Then now let's consider that the quorum storage or little list application. What exactly does this kind of theorem means? Okay. So now again we have we have three servers, and then the R and W are both equal to 2 because we want to satisfy strong consistency. And then again we have two clients. So at first this client write to WK equal to 1, and because W equals to 2, so what you have is that, okay, this server got it, and then this server got it, and then they both respond acknowledgement to this client. Okay, so that's good. Then now we have a partition tolerance. So somehow the rightmost client, rightmost server, and then client cannot communicate with the rest of the system. Then in this case, the client said, hey, actually I'm not able to receive two responses right now. Remember, R also equal to 2. I need to do that. I need to wait for 2 responses. Then now that this client kind of have two choices. If I want to keep waiting, then that's kind of like favoring consistency over availability, because it's possible that this response will never be available because that the communication, this one, cannot occur. Okay. On the other hand, the client can also say that, hey, no, you know what? I don't really care about consistency. I can return right now, because at this server on the right hand side, it doesn't really receive 1. But if you care about availability, this server can directly return to this client, say that, hey, this is what I get. If you want it, you can return. And then in this case, you don't have consistency, but you have availability. Okay. So this is kind of like how CAP theorem may applies to this leaderless storage. At this point, you might say, wow, okay, what did I just hear? But because I CAP theorem sounds like so simple, like all the model are clean and then I prove are very intuitive. But then I can tell you that actually it's not very easy to apply to practice. And then there are tons of interpretation, and some of them doesn't quite make sense. And then if you read some article online, you will see that okay, the most straightforward interpretation or application of CAP theorem is that if I cannot achieve all three together, let me just pick two. Okay, so that you will see a triangle, you will see consistency, availability. Oh, sorry, this should be P, like the partition tolerance. And then they will classify their system, say that I have a CA system, I have a CP system, I have a AP system. But then actually this is not a good way to interpret or like to introduce your system, because that especially in the nature of distributed system, especially modern applications, you can never satisfy partition tolerance, because partition tolerance is that very common. Okay. And then some of the people would just say that, okay, if I decide to be a CP system, then I always forget about availability. But like when you think about your system, what does it mean by sacrificing availability? Does that mean that some of the operation may never terminate? Or does that mean that you will never get response? And all of them are not very good choices when you come to the practical system. Okay. So that pick two out of three, that's a very bad interpretation. And then some of the claim in the paper, you will say that, oh, actually I can achieve all three together. Actually, that we don't need to worry about CAP theorem. We can bypass it. However, I will mark it as a question mark. That's the claim is not very precise, because it really depends on what kind of models you are deal with. Many of those papers it's kind of like said that okay, we can never have this kind of very ill form of a partition that's described in Nancy Gilbert and Nancy's paper, which is a fine claim. But then it doesn't really mean that you achieve three things together, because in the original paper there was a very precise definition. Then I think that personally I would like to see that we are basically dealing with a different model, and then it's not like okay, I can in this model I can achieve all three things together, because that's basically the theoretical proof that you can never bypass it. Okay. And then I would say that this is the final interpretation is that most practitioner think is the right way to use the CAP theorem is that when network is not partitioned, you want to achieve both consistency and availability. But in the unfortunate event that network is partitioned, for example, the leaderless, the current storage example I show you, at that point of time, you should choose between consistency and availability. Okay, and that's the kind of takeaway is that you need to understand the model, and then you need to think about your application. What are the properties that you can never satisfy, and all that, what does it mean to sacrifice something? Okay. And because there were so many confusions, so Eric Brewer actually wrote another article, said that okay, now let's look at this again. What does this mean? What are the rules? And there are lots of very good points. For example, say like CAP, but like one of the important metrics in practical system is latency. So how does a CAP related with latency? And then the second one is some of the confusion I mentioned earlier. I will explain more detail in the next slide. And then Eric Brewer also talked about that, okay, in practical system, even though partition is rare, but there are some mechanism that we can actually manage partition or we can do some recovery. So it's not always like when there's a partition, I have to make choice that what I'm doing, okay? And then that's a kind of the thing you want to think about practical system. Practical system, real world system is never that clean, and then there are lots of dimensions that you can deal with, and that's also the fun part. So the one point I want to focus on is this CAP confusion. So it's that the this why pick 2 out of 3 is confusing or that is misleading, because that whenever there's no partition at all, then you can have both property. But some of the prior interpretation is that I don't really care about partition or not. I just forfeit or sacrifice one of the C or A, and then that's not a correct or that's not an ideal trade-off. And then the second one is that you make a choice, but that you can make that a very fine granularity. Okay, so for example, that the distributed storage part, that you can do this choice for every operation. And then if you are thinking about like more complicated distributed system, you have lots of different storage, you have a cache, you have different kind of microservice, and then at different component of the system, you can make a different choice. Okay. And then the third one is that the way the CAP theorem was stated was conjectured. It's always binary. Either you have C or you don't have C. Either you have A, you don't have A. But in practice, it's more like a continuous spectrum. And then how to model that? That's actually a very good open question. And I also want to introduce you like this paper, this article by Martin. It's a critique of the CAP theorem. And that the paper serves a very good introduction on what the CAP theorem is, what's a model, and then more intuition. But the one thing I like the most is that Martin goes into a detail to explain that empirically what kind of system properties that we will observe, how is it different from the theoretical model. And like one on the one hand, it's very good to have a formal model, and then you have a clean model, have a clean proof. But like sometimes you want to understand the difference between the model and practical system. Okay, and then if you read one paragraph, you will see that okay, the way the availability is defined actually doesn't really match the practical experience, and then there are certain kind of a concept of contradiction, and then that will lead to the conclusion. Martin's key conclusion is that okay, yes, CAT theorem, the modeling, the proof is very true, but it's not clear how to apply that in practical system. So based on his own experience, Martin gives us several alternative way to interpret or like to use CAT theorem or even like generalize, extend that. And then I encourage you to read. It's a very fun read. Okay. So the takeaway is that I want to know about this CAT theorem, and if you go to like kind of an industry interview, actually people ask about this. Okay, so I want you to know about the model, and then the practice, and then high level idea of the proof. And if you want to be a practitioner, or if you are a practitioner, then one thing to remember is that there are tons of very good result, good paper from academia, but you will want to understand the abstract models and then the theorem, how what does that mean, and then the connection between the model and then practical system, and you want to have a correct interpretation. Okay, so if you don't apply it correctly, then you may give us something too fast. Then if you are in academia, you want to do some practical research first, identify real problem. I think like CAT theorem actually is on a very uh, good has a very good contribution because it tried to give the foundational result for practical system. But once you have a clean model and clean proof, and it's also good to think about that in terms of modeling, what is a more realistic modeling and how does your model match the empirical experience? And then the final ones, I think about application. Once we have the result, very cool theorem, but like sometimes maybe we want to communicate a bit better so that a practitioner and an industry know like how to really apply this cool result. Okay, so that's all for today. Thank you.